Dear students, in the last class, we have studied about the applications of crystal field theory in the color of the complexes and also the magnetic properties of the complexes. So today we take the another important aspect of the metal complexes, that is stability of metal complexes. When I speak about the stability of a metal complex is the existence of the complex under favorable conditions without undergoing decomposition and having considerable shelf life period. So the statement itself says if a compound is to be stable, it should have these conditions. That is, the compound should not undergo decomposition and it should have a sufficient shelf life period. Now, the term stability of metal complexes cannot be generalized because the complex may be stable to one reagent or one particular condition and may decompose in presence of another reagent or another condition. So this is also very important, the point to be noted. So the stability, it is not a permanent aspect of the metal complexes. It is in general even for the human beings also. The stability of metal complex, it cannot be generalized. That's what it says, because the complex may be stable in one reagent or a particular condition, or it may decompose. The same complex may decompose in presence of another reagent or another condition. The stability of metal complexes can be explained with the help of two different aspects. Number one, thermodynamic stability, and number two, kinetic stability. So, the thermodynamic stability, if a compound is to be stable, we know that the free energy of the system should be less and entropy should be more. Then the reaction turns into the product. The same thing here also we say about based on the thermodynamics. We have kinetic stability. So the kinetic stability refers to the compound must be the labile or inert based on its the kinetic aspects. This we learn in detail in this particular chapter. Coming to the thermodynamic stability of a complex. Thermodynamic stability of a complex exists under equilibrium conditions. This is very, very important. So, if a system is in equilibrium, then only this thermodynamic stability comes into the consideration. That's why it says thermodynamic stability of a complex exists under equilibrium conditions. It determines the extent to which the complex will be formed or be converted into another complex at the point of equilibrium. It is represented by formation constant, or it is also called stability constant, which is denoted by the letter K. It is directly related to the metal ligand bond energies. In general, metal complexes are prepared in aqueous solutions wherein metal cation gets hydrated to give aqua complexes of the type MH2OX times whose oxidation state is N+. When a ligand replaces water molecules from one aqua complex ion, a new metal complex is formed and equilibrium is established between the two. If I take the aqua complex MH2OX times having the oxidation state N+, when ligand L comes, then this MH2OX minus 1 ligand attaches, oxidation state will be N+, giving out a water molecule, where X is the number of water molecules, N is the oxidation number of the metal cation, L is the neutral and monodentate ligand. Now the above reaction is in equilibrium. So you can apply the law of mass action to this equation. So for above equation, the law of mass action applying, we get that K is equal to active mass of H2O, active mass of a complex of the product divided by the active mass of the complexes of the reactants. So here it is the active mass of MH2O X minus 1 into L raised to N plus divided by active mass of MH2OX times whose oxidation state is N plus into active mass of L. If I take a generalized equation, that is M reacts with L. Here M means it is not a metal, it is the metal ion whose oxidation state is N plus, which is generally written as M. So M plus L gives Ml is the complex and the reaction is in equilibrium condition. It is a reversible reaction. Hence apply the law of mass action. So therefore we get the equilibrium constant, which is also called the formation constant or stability constant. Sometimes the formation constant is given as Kf or the stability constant is given as Ks. Both means the same. Here the stability constant of this reaction is the active mass of the product, the complex, that is Ml, divided by active mass of the M into active mass of L. It is noted that, it is to be noted, higher the value of the formation constant or stability constant, the greater will be the stability of the complex. Very, very important statement. If the formation constant or stability constant is greater than 1, it indicates that at equilibrium, the activity of the complex Ml is larger than the product of activities of the metal ion and ligand. This indicates the ligand L binds to the metal ion more strongly than the water and hence ligand L is a stronger ligand than water. If Kf, that's a formation constant, is less than 1, it indicates the ligand L is weaker than water. Thus, the stability constant is used as a measure of thermodynamic stability of the complex. Consider the formation of the complex MLN, where by the combination of metal ion M with the ligand L, and N is the coordination number. The reaction is M plus N number of ligands NL, which is in a reversible reaction, forms a complex MLN, where N refers to the coordination number. This reaction proceeds in the following steps. In the first step, M combines with the L to form Ml. Then Ml combines with L to form Ml2. Then Ml2 combines with the L to form Ml3. In general, Ml n-1 combines with L to form Mln. So to form up to the stable complex, this reaction proceeds. Now for all these reactions, if I calculate the stability constant, then for the first reaction, which is known as K1, is equal to active mass of Ml divided by active mass of M into active mass of L. For the second reaction, it is K2, the active mass of Ml2 divided by active mass of Ml into active mass of L. For third reaction, the K3, active mass of Ml3 divided by active mass of Ml2 into active mass of L. In general, I can write the stability constant for the generalized reaction, that is Kn is equal to active mass of Mln divided by active mass of Mln-1 into active mass of L. There will be n such equilibria which represents the coordination number of the metal ion. There it's known as K1, K2, K3 and so on up to Kn are known as stepwise stability constants. K1, K2, K3 and so on, they are known as stepwise stability constants. It is noticed that K1 is greater than K2, which is greater than K3 and so on, greater than Kn. This is because the ligands which are already coordinated to the metal ion will repel incoming ligands towards the metal ion due to the Coulombic repulsions. This trend is illustrated by taking the formation of cadmium complex with ammonia and copper complex with ammonia as examples, where log K values for different steps are considered. Here, the K values gives the 10 to the power values, whereas the log K values gives a numerical numbers. So generally, the the stability constant is expressed in terms of the log K values. Consider the complex, the cadmium tetramine 2+. This cadmium tetramine 2+, it takes log K1 means the copper ion takes 1 ammonia to form CuH2O thrice NH3 complex, and log K1 value is 4.3. Okay, and for log K2 means the copper CuH2O thrice NH3 complex takes 1 more ammonia and forms CuH2O twice NH3 twice, the 2+ complex. The equilibrium or the stability constant for this reaction is 3.6. So similarly, for log K3 is 3.1 and log K4 is 2.3. That means the stepwise stability constants goes on, decreases from first step to the last step till it accepts all the ligands to form a stable complex. Similarly, if you take the cadmium complex, that cadmium CdNH3 4 times, the 2 plus ion. Here the log K1, K2, K3 and K4 values are 2.6, 2.1, 1.4 and 0.9. Now these values are known as stepwise stability constants. Now consider how to calculate the overall stability constant or cumulative stability constants. For this, consider the generalized equation for the formation of a complex MLN. That is, M reacts with n number of ligands to form MLN complex, where n is the coordination number, L is the ligand and M is the central metal ion. It is not the metal. The equilibrium constant for overall reaction is given as M combines with L to form ML. This is one way. And the same M may combine with 2L to form ML2. Similarly, M combines with 3L to form ML3. So, M combines with 4L to form ML4. In general, M combines with NL to form MLN. The overall stability constant or cumulative stability constants are shown by the letter beta. These beta values are also the stability constants. These are overall stability constants. The K1, K2 are stepwise stability constants. Now for the first reaction is known as beta 1. Beta 1 is equal to active mass of Ml divided by active mass of M into active mass of L. For second reaction, beta 2 is equal to active mass of Ml2 divided by active mass of M into active mass of L raised to 2, because here 2L are there. Similarly, for the third reaction, it is beta 3 is equal to active mass of Ml3 divided by active mass of M into active mass of L raised to 3. In general, beta n is equal to active mass of MLN divided by active mass of M into active mass of L raised to n, where beta n is known as nth overall stability constant or cumulative stability constant. Since stepwise stability constants K1, K2, K3 up to Kn and overall stability constants beta 1, beta 2, beta 3 and so on beta n describe the same chemical system, these two must be hence related to each other. Now let us study what is the relationship between overall stability constant beta and stepwise stability constant K. Now consider for this a reaction M combines with 3L to form ML3. For this reaction, beta 3 is equal to active mass of Ml3 divided by active mass of M into active mass of L raised to 3. For this reaction, multiplying the numerator and denominator by active mass of Ml and to active mass of Ml2 and rearranging, we get beta 3 is equal to active mass of Ml3 divided by active mass of M into active mass of L raised to 3. This into active mass of Ml1 into active mass of Ml2 divided by active mass of Ml1. Ml1 can also be written as only Ml also into active mass of Ml2. And rearrange this. So we can rearrange this as active mass of Ml divided by active mass of M into active mass of L into active mass of Ml2 divided by active mass of Ml into active mass of L into active mass of Ml3 divided by active mass of Ml2 into active mass of L. These values are nothing but they are K1, K2, K3. So beta 3 is nothing but it is the product of the stepwise stability constants, that is K1, K2 and K3. In general, for the nth overall stability constant is given as beta n is equal to K1 into K2 into K3 and so on up to Kn. Since the beta values are the powers of the 10, it becomes, rather than to explain more easily, we take the log in both the sides. So taking log both the sides, we get log beta n is equal to log K1 plus log K2 plus log K3 and so on log Kn. Thus, log beta may be used as a measure of stability of the complex. Consider, let us take an example. Consider the complex, the tetramine copper 2 ion. As it contains 4 ligands, it involves 4 steps. That is, beta 4 is equal to K1 into K2 into K3 into K4, or log beta 4 is equal to log K1 plus log K2 plus log K3 plus log K4. The values for this is already given in the previous slides. So substitute those values here. We get 4.3 plus 3.6 plus 3.1 plus 2.3 gives 13.3. So therefore, overall stability constant of cupramonium ion is 13.3. Similarly, consider the complex, the cupramonium cadmium ion. So for this also we have, it involves the 4 steps because the coordination number is 4, and add all the K1, K2, K3 and K4 values which are given earlier. So by adding all, we get 2.6 plus 2.1 plus 1.4 plus 0.9 gives 7.0. Here also once again, greater the value of overall stability constant, greater is the stability of the complex formed. In the above 2 examples, so it is concluded that the cupramonium ion is more stable than the cadmium complex. This is what is written. This can be confirmed once again by adding the hydrogen sulfide to the above 2 complex, where the copper complex will not precipitate as cuprous sulfide because ammonia is strongly held, so there is no formation of a precipitate of the copper sulfide. But whereas the cadmium complex gives yellow precipitate of cadmium sulfide because its a complex is less stable. So this is another important aspect. So to confirm among these two, which is more stable complex. Now coming to the another aspect, that is kinetic stability. Kinetic stability is related to the reactivity of the metal complexes in solution. This is very important, in solution. Of course, all the complexes generally we carry out in solutions. Kinetic stability is related to the reactivity of the metal complexes in solution. It deals with the rate of the reaction, its activation energy, etc. It is also related to how fast a compound reacts rather than how stable it is. So this is very important as far as the kinetic stability is concerned. So the compound may be more stable, but if it is not going to react to form a product, so then we say it is kinetically less reactive. Therefore, kinetic stability, it tells us about how fast a compound reacts rather than how stable it is. It aids in determining the rate at which the reaction occurs to establish the equilibrium. So the reaction, it has to attain the equilibrium to the faster extent. This is what the rate. At what rate it establishes the equilibrium to the faster extent. The term kinetic stability of complexes is classified into the two, that is called the labile and inert, by Tube on the basis of rate of the reaction. When the rate of substitution of ligands is high, the complex is said to be labile, or it is kinetically very fast. Example: the copper complex of the formation of the cuprammonium, the tetramine diaqua copper 2 complex is labile. That means it is more reactive. In aqueous solution, the complex is blue in color. When concentrated HCl is added to this solution, the solution turns green, giving rise to CuCl4 2- complex. So it is tetrachloro copper 2 complex. In inert complexes, the rate of exchange of ligands is very slow. In the above case, the rate of exchange of ligands is very fast. That's why the above complex is an example for the labile complex. In inert complexes, the rate of exchange of ligands is very slow. The example: the cobalt complex CONH3 6 times 3+ reacts very slowly and no reaction takes place at room temperature when concentrated HCl was added to the aqueous solution. So when the concentrated HCl is added to the cobalt amine complex, no reaction takes place at room conditions. However, only one ammonia ligand was found to be substituted by the Cl ligand when the aqueous solution of the complex was heated with 6m hydrochloric acid. That is 6 molar concentrated hydrochloric acid. This shows that the above complex is inert in presence of the acid medium. As a rule of thumb, it says a metal complex is said to be labile if it reacts within 1 minute at 25 degrees centigrade, and if it takes longer time, it is considered to be inert. This is a statement. It says to which complex I should call it as a labile complex and to which complex I should call it as an inert complex. What is the condition for that? So as a rule of thumb, it says the condition to become a labile is the complex is said to be labile if it reacts within 1 minute at 25 degrees centigrade. And if it is not going to react within 1 minute, that complex is considered as inert complexes. The stability and reactivity of metal complexes are described in thermodynamic and kinetic terms respectively. That is, the term stable and unstable are related to thermodynamic aspects, whereas labile and inert terms are related to kinetic aspects. So, if I want to say this in the case of a stability of a complex, if I say the compound is more stable or unstable, these terms are used for as the thermodynamic aspects. If I want to say about the kinetic way, whether the compound is stable or inert, so there we use the terms labile and inert. Thermodynamic stability refers to the energy change that occurs when starting materials are converted to products. The change in free energy is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy of the reaction, T is the temperature, and delta S is the change in entropy of the system, which is also nothing but minus RT ln K, where K is known as the equilibrium constant for the reaction. In this case, it is called stability constant for the reaction. Kinetic stability refers to reactivity or ability of the metal complex to undergo ligand substitution reactions. Complexes which undergo extremely rapid ligand substitution reaction are referred to as labile complexes, and complexes that undergo extremely slow ligand substitution reaction are called inert complexes. It is to be noted here, sometimes the thermodynamic and kinetic stability of complexes are parallel to one another, but often they do not. Let us take an example. Consider the reaction. Nickel ion combines with 4 cyanide ions to form tetracyanonickelate 2 complex. The overall stability constant for the reaction is, that is, beta value is 10 raised to 22 or log beta is 22. This indicates the complex is thermodynamically very stable because the log beta is having higher value. Now, this tetracyanonickelate 2 complex to this, when I add the cyanide ion where the carbon is a radioactive carbon, that is carbon 14 is introduced in this cyanide, then it forms readily the complex NiCN thrice, and the cyanide ion, one of the cyanide ion is replaced by the another cyanide ion which contains carbon 14 isotope. The rate of exchange of cyanide ligand with carbon 14 cyanide is very fast. Therefore, this complex is kinetically very labile. So, this complex, that is tetracyanonickelate 2 complex, is thermodynamically stable as well as kinetically labile. Thus, the complex is thermodynamically very stable and kinetically labile. Consider another example, that is hexamine cobalt 3 complex. This complex is thermodynamically unstable as the complex decomposes very rapidly in acid medium with the rate in the order of 10 raised to 25. So its decomposition rate is very fast, that is 10 raised to 25. It's given here. So the K value. However, no ligand substitution reaction is found when the complex is kept in acid solution for several days. This shows that the complex is kinetically inert. Thus, the hexamine cobalt 3 complex in acid medium, it is thermodynamically unstable and kinetically it is inert. From the above two examples, it is concluded that kinetically inertness or lability of the complexes has nothing to do with the stability as derived from thermodynamics. This statement is very important. This is what I have said in the very first statements in this particular class. That is, the above examples, it is concluded that kinetically inertness or lability of the complexes has nothing to do with stability as derived from thermodynamics. So here, what we have discussed so far have given these things in terms of small points. It says the defining stability. The statement that a complex is stable is rather loose and misleading very often. That's why I have said in my very earlier. It means that the complex exists and under suitable and required conditions, it can be stored for a long time. But this cannot be generalized to all complexes. One particular complex may be stable towards a reagent and highly reactive towards another. This is what I have explained, even these things. Coming to this slide, that is thermodynamic stability. As far as complexes in solutions are concerned, there are two kinds of stabilities. One is thermodynamic stability, another one is kinetic stability. Thermodynamic stability is a measure of extent to which the complex will be formed or will be transformed into another species when the system has reached equilibrium. Kinetic stability refers to the speed with which the transformations leading to equilibrium will occur. Under this, the rates of substitution, racemization, and their mechanisms. The factors which are affecting the rates of reactions are also studied in this kinetic stability. Now, whatever we have discussed, all these things are once again rebrushed in these slides. I have given the stability constant or formation constant for the various reactions K1, K2, K3 and so on. And also the below it shows about the overall stability constant for the reaction. So overall stability constant for this reaction, that is beta n is equal to active mass of mln divided by active mass of m into active mass of L raised to n. That n is missing here. Active mass of L raised to n. So these are the equations concerned to the cadmium as well as copper complexes, how the formation constants are calculated and how the values are given. As I have said, in case of the cadmium complex, the value is given as K1 is equal to 10 raised to 2.65, K2 is equal to 10 raised to 2.10, K3 is equal to 10 raised to 1.44. Instead of writing 10 raised to this, we are using the values, the log. So here log K1 becomes 2.65, log K2 becomes 2.10, and so on. Below I have written the equilibrium constant values, how to calculate. So in case of Cu2 plus NH3 gives rise to CuNH3 raised to the oxidation state 2 plus. So if they ask, write the stability constant equation for this reaction. So the stability constant for this reaction is K1 is equal to active mass of CuNH3 raised to 2 plus divided by active mass of copper ion Cu2 plus into active mass of NH3. So like this, you must able to write the stability constant equations. Here, these are called the overall stability constant. This also I have shown, I have explained in the earlier. Now, here kinetic versus thermodynamic stability. The terms labile and inert refer to the reactivity of a complex only, not to be confused with its stability. An inert complex may be stable or unstable. Similarly, a labile complexes may be stable or unstable. This is what I have said in my last statement. So, the kinetic stability and thermodynamic stabilities, they are two different entities. Dear students, go through these aspects and try to learn about these mathematical things. It is very easy if you read for 2 to 3 times. Thank you.